So last lecture we talked a lot about time-stepping schemes, introduced some of the basic ideas of using, developing these Runge-Kutta methods or multi-step schemes, something like the Adams family of Adams-Bashforth, Adams-Moulton, which are multiple-step schemes. One of the important issues in all of this is that these set up iteration schemes. Now, iterations are really nice for the computer to do because you just set it in a loop. It iterates. Now, the question is about the iteration scheme you actually set up. Is it stable? There's a lot of iteration schemes where you can start an iteration going, and the final result is that this thing blows up to infinity. Now, if that's the case, that's what we call an unstable scheme. The last thing you want to do is develop an iteration scheme to solve a problem, and the solution goes to infinity. It's not going to work very well for you. Okay? So what we want to talk about are two issues: accuracy and stability. So, by the way, I put all my notes online. Everybody, if you find them on the web page, they're there. All 140 pages of it. You can download it at your leisure, and it should be good to go. So, if you have any problems downloading, let me know. But otherwise, everything's there now. And then the homework will be posted probably within, certainly by the end of the week, so you can start thinking about that stuff. All right. Any scheme you build, these are two fundamental issues you have to think about. Obviously, you want high accuracy. Obviously, you want stability. The typical problem is these often don't go hand in hand. Like if I get a really accurate scheme, it's stable. No, actually, it's typically the opposite. A really stable scheme often can be very inaccurate. Or if you have a really accurate scheme, there's often some instabilities associated with it. So there's a little bit of a trade-off you're doing here. You're trying to develop a scheme that kind of gets you both as best as you can. Okay? So, like I said, it's very rare that you get both of these two working together so that you get better accuracy and better stability at the same time. Usually doesn't happen for most schemes. So we're going to address the two issues separately. So the first part, we'll talk about the accuracy. How do you talk about accuracy of a scheme? And then the second part, we'll talk about then what is the stability associated with those schemes. Remember, we're going to consider still the simple, I guess, system of differential equations like this. Okay? Whenever we solve a PDE, we're always going to reduce it down to a system of differential equations. That is not only the trick to do numerically, but it's always what you do analytically. If you've taken a course on the theory of partial differential equations, the whole game you're playing, whenever you solve a PDE, is you reduce it down to ODE. The whole deal then with an ODE is then you reduce it down to algebra, you solve it, and then you bring it back up. Okay? So that's, we do the same thing computationally then. All right. So we're going to look at this equation. And let's start off with something simple, which is the solution y at t plus delta t. Let's just take this thing, and let's just do a Taylor expansion. At this point, this has nothing to do with this equation, but just take this quantity, do a Taylor expansion. Almost everything we're going to do when you do an error analysis is going to do Taylor expansions. Okay? So when you do that, you expand around y of t. What you get is the following: y of t plus delta t dy dt plus delta t squared over 2 something like this. This is exact. Where c, the constant c, is a value contained within t of n and t of n plus 1. This is where, I guess in this formulation, it would be between t and t plus delta t. So this is an exact formula. You may have seen it in calculus at some point. We've just expanded this thing out. This is our error, if you want to, our remainder that was often called in calculus. And we don't know where c is. We just know it's in this interval. Okay? But that's an exact formula. Let's see what we can do. All right. Now notice a couple things here. This was just an expansion. What is dy dt? dy dt is this f. So we can plug this right into there. And what do you end up with? Y t plus delta t is equal to y of t plus delta t f t y of t plus, and just do that. This gives us back the Euler scheme that we started with yesterday. My solution in the future is what it is now plus delta t times the function f evaluated now. That's it. But notice, unlike last time where we sort of just did this, we used the derivative approximation. Now I'm being a little more careful. I've kept in this term here. Now what O means is the order of this term is delta t squared, scales like delta t squared. And specifically, it is this quantity right there. Okay? The important thing is when you have just delta t, as you make it smaller and smaller, this gets smaller and smaller. Faster than this. So this goes like delta t. So if delta t is 10 to the minus 2, then this thing is going to be 10 to the minus 4. So this should be a lot smaller. We can think of it as an error, and we can throw it away. And that's exactly what we do when we do an Euler approximation. We just say, okay, that's going to be really small. Let's trash it. So the question is, what about the error you induce in the scheme then? Because we're going to throw that away. We're going to be left with this. This is exact. As soon as I throw that away, it's an approximation. And then the question is, if I do that, what is the error then in that approximation? All right, so here's how we think about error. And there's two things about error that we need to think about. One is global error, and the other is local error. What global error is going to be is the error I basically pick up as I run this thing for a long time. Suppose I want to run the solution from time 0 to time 100. So over this whole time I run it, what is the error I get at the end? Local error is just how much error do I pick up over one small delta t. Okay? All we really care about is the global error. This is the cumulative error you have in your code. Okay? It's going to be the most important thing. And that at the end of the day, so if I start off my solution at time 0 and at time 10, I'm really concerned about is how much error I've made in the whole thing versus just a small delta t of it. Okay? But we can define each one of these things. So the global error is defined as the following. Is equal to global error is just the exact solution evaluated at the final time, call it t of k, minus your numerical approximation at y at time t of k. So this is your numerical solution. This is your exact solution. Now, of course, you can also ask, well, if I have the exact solution, this is stupid. Right? But the point is that you typically don't have it. This is just a definition. We'll play around with it, and you'll see how the results go. Okay? In general, you don't know what the exact solution is. This is why you're throwing it on the computer in the first place. Okay? But that's your numerical solution you get from this iteration process. The local error, it's epsilon k plus 1, let's call it, is it's the exact solution at t of k plus 1 minus this quantity here. What this is the numerical approximation over one step. Remember, this is the exact solution, y of t of k. That's the exact solution at time t of k. And if I add this, remember, this is like a one-step formula. This here gets me to my next time, delta t times 5. This is what we talked about with these Runge-Kutta methods. All I have to do is take my current time, add a little something, that gives me my future solution. So this is the numerical approximation of my future solution, okay, over 1 delta t, and I subtract it from what my actual solution should be. So this is only giving me an error over just one step. This is giving me the error over the whole way, all the way to t of k, starting from the beginning. Okay, so those are the two definitions. And we can calculate these two quantities for the Euler scheme we've developed here. We can see what happens. So let's talk about first the easiest thing to calculate. For the Euler scheme, let's calculate the local error. The local error, then, is the following. Let's go back and look at what the local error is over one step. Here's my step going from time t to t plus delta t. So over one step delta t, I'm basically throwing this away. So what is my error? That term. I've neglected this term. So that's my local error over one step. Okay, that's this piece right there. That's what I'm throwing away. So this one is easy. We've already done it. So when you do Taylor expansions, it gives you this already. And again, the important thing is it goes like delta t squared. This value here, we assume, is sort of like some order 1 quantity that's 2, 1.5, 1.382. Who cares what it is? It's just some order 1 parameter. The point is that how does it scale as I change delta t, which is something you have control over. Okay, that's the local error. So you can see already the error analysis that comes up from this stuff is all going to be based on this Taylor's expansions. Because what we're going to do is develop these schemes. You're going to truncate it at some point. And wherever you truncate it in the Taylor series, that's your error. And this is what you're throwing in here as your local error. And then, with the local error in hand, you can calculate the global error. Now, the global error we can calculate by saying, let's run this thing on some interval from time A to time B. And let's take k steps. Okay? So we're going to take k steps going from A to B. So that means the following, that delta t times k is equal to b minus a. That's all I'm saying. K steps. So I pick my delta t so that in k steps I span this interval. So now, what is the global error? All I have to do is sum up the error over this whole thing. Every time I take a step, I make an error, which is just my local error. And what I do for the whole thing is I just add up all the local errors that I make throughout the whole time. So that's it. Now here's something important to notice. Why don't we approximate this by, I don't know what all these are, but I'm summing up k of them. So suppose I take some average value of this thing here. In other words, if I knew what the average value of the second derivative was over the whole time span, I could pretty much write this as so if I knew the average value of this over all the k steps, I could take it out of the sum, and I'm stepping over k times. So basically, this just becomes k of these. But what is k? Well, k is from here. It's b minus a over delta t. So if I put in that to there, what I find then I get b minus a over 2. I get 1 delta t canceling with this up here. And so I end up with this formula here. Notice, this now is order delta t. So your error, your global error is delta t. If I take a step size of 10 to the minus 2, my delta t is 10 to the minus 2, then I end up with an error that's the same size as that. 10 to the minus 2. It's not very good accuracy. Okay? This is why there's the fourth order Runge-Kutta. In MATLAB, it's called ODE45. Okay? So when we come over here, this is one of the standard ODE solvers that we're going to use. And we'll talk about this in class later more. But ODE45 is a fourth order Runge-Kutta. What the 4 and the 5 represent is the 4 represents global error, the 5 local error. Your local error is ordered delta t to the 5th power. Your global error is ordered delta t to the 4th power. So if I take that same time step, 10 to the minus 2, this ODE45 scheme will give me accuracy of 10 to the minus 8 at the end of this interval I run it. Compare that to this, which gives me accuracy of 10 minus 2. This is a significant improvement in the accuracy. Okay? This is why you develop these schemes. Because if you need something that's 10 to the minus 6 accurate, what's the cost? If you do it with the Euler method, if you need something that's 10 to the minus 6 accurate, you're going to have to take time steps of 10 to the minus 6. Okay? Whereas, with the ODE45 scheme, if I need 10 to the minus 6 accuracy, all I've got to do is take steps of like 10 to the minus 2. That'll actually get me 10 to the minus 8 accurate. So this thing here is taking time steps of 1,000 times bigger. So it's going to run 1,000 times faster. Okay? That's significant improvement. Remember, though, in the ODE45, remember there's a 4-step process. So maybe we say it's 1,000 times faster, but I have to do 4 computations per step. So maybe it's still cut that down by a factor of 4. It's 250 times faster. This is the kind of thing you've got to think about when you build codes. If you can get a code that runs 250 times faster, you write that code. Even if this one will give you the right answer. It's called the dumb way, the smart way. All right? All right. I like to say in numerics that although you can get to the right answer and you can say my code works perfectly, that gives me the right answer. If you're doing it in a silly way like this, you could say that, well, you're really wrong in some sense, right? You need to use the tools that are best suited for the job. Otherwise, you're really losing precious time or resources on doing dumb things. Okay, so that's the accuracy issue. And it actually follows fairly straightforward from these Taylor expansion arguments. Now, one of the things you notice right away is you would be tempted to conclude from what I just said about this ODE45 or even this thing here is that, oh, if I want to be really accurate, all I have to do is keep cutting delta t down. Make it smaller and smaller and smaller. This error is going to 0. So your conclusion is that if I keep making smaller and smaller time steps, I'm going to get more and more accurate, whether I'm using this scheme or this scheme here. It's mostly true. But the fact is, your computer has roundoff in it, roundoff error. Your computer only computes typically to 16 digits. It's called double precision accuracy. It's only going to keep around 16 digits. Some software packages will allow you to go higher than that. And some things like Maple and MATLAB will allow you to pick as many precision as you want. How many digits of precision do you want? But the typical thing to do when you do computations is double precision gives you 16 decimal places of accuracy. Okay? Now, given that, any number you give into the computer, 2, is accurate to 16 decimal places. Okay? 2 is not really 2. It's the 16 decimal places, it's 2. But it's not 2. Okay? So the question is, how does that play into this? Well, it's another source of error. And let me just show you that the simple-minded thinking of just taking smaller and smaller time steps can actually get you into problems. So let's talk about roundoff. So numerical roundoff. In particular, let's just think about a derivative. We say that we can approximate this derivative by some kind of slope formula. This is what we learned from calculus. That the derivative is equivalent to an instantaneous slope. Well, again, and my point last lecture on Monday was that there is no such thing as instantaneous or infinitesimal in the computer. What you've got to do is you've got to step back and say, okay, the only thing the computer could do is the add, subtract, multiply, divide. I have to work with discrete quantities. So we said, let's make this approximation. But when we make this approximation, what I just pointed out is that you also pick up a local error, which is the truncation error. Now, suppose I go to the computer. This is all just on paper, pen and paper, and works out nicely. Now I go to the computer, and I say, let's evaluate this. All right? So if I go to evaluate any one of these numbers, for instance, this one here, what do I get? I get the actual number, but it's only accurate to the round off. So, I get the number, but this is like 10 to the minus 16th. It's only accurate to 10 to the minus 16th. So when I actually have the representation of that number in the computer, it's this number here, but I've made a mistake. I have a round off term that goes with that. Okay? So now we can say, let's go back and then think about this. So that's your round off. So now when I go to think about evaluating the derivative of something, what do I get? Well, I actually get the numbers evaluated in the computer plus some error. And the point about this error is that it's made up of two parts. Now, it's made up of the round-off error plus truncation error. We've already talked about the truncation error. That was what we've just spent the time talking about. And this is just due to the Taylor expansion. But then there's this round-off error. And here's the important thing that we're going to observe about it, is that if these two errors are there, this argument about just taking smaller steps is no longer going to work. So let's calculate what this round-off error is, or this total error. The round-off error is just the error you make in evaluating the actual quantities you were trying to evaluate. Right? So here's the mistake you made from trying to evaluate the solution at y of n plus 1. Here's the mistake you made in trying to evaluate it at y of n. Plus the truncation error. Well, the truncation error was that there. Okay, so there's your total error. Now here's the observation. Let's try to find what's the maximum error. Let's just try to get a ballpark figure of what goes on here. Let's suppose that my round off is of a certain size. In particular, suppose I can bound how big this error is to some absolute biggest size. So my round off error is below this. Both pieces of the round off error are below some absolute big size. And by the way, this error, round-off error, we know what it is. It's 10 to the minus 16. It's the double precision for MATLAB, for instance. So we know what that is. That's as big as that error is going to get. It's not going to be 10 to the minus 8. We know that MATLAB collects it down to 10 to the minus 16. That's what the accuracy is. And let's suppose, in addition, that the maximum value of this derivative on the interval that we're looking at is just y, is m. So in other words, suppose I can say that this derivative term, the biggest it can be is m. Again, we're just going for just trying to get a feel for how big this stuff is. Then the error, the absolute value of the error, is less than or equal to e of r over delta t plus delta t squared over 2 m, which in total gives 2 e of r delta t squared m over 2. So there's a total error. This is kind of the maximum size of it. Yeah?
Minus sign on the top.
That's a good question. Doesn't matter so much, but yeah, in the notes I noticed I have that minus sign too, and it doesn't matter for what we're going to do, but that might be 25 cents coming your way. We'll see. So, okay. So that's what we get. Now, suppose I were to plot this. Oh, that's delta t squared there. Suppose I were to plot this as a function of delta t. And let's look at the constitutive pieces here. Here is this error as a function of delta t. So first of all, it's made up of two pieces. There's this 1 over delta t piece. Well, what does that look like? Well, that looks something like this. This is the error due to the round-off. And then there's a piece that goes like delta t squared. So this is the error we were talking about with truncation. The idea was, as your delta t gets smaller, you just fall down this curve. Error gets smaller and smaller and smaller, so it takes small delta t. But the round-off gives you this structure. So your total error actually does something like this. So if you keep taking smaller and smaller and smaller delta t, eventually you're going to end up over here, where now your round-off error is killing you. Okay? So it does not make sense to keep taking smaller delta t. In fact, what you want to work is, there's the sweet spot there and above. Otherwise, round-off is just starting to get you. Now, how do you find that spot? Well, you can get an estimate of it by just taking the minimum of this curve with respect to delta t, setting it equal to 0. Minimum of curve, take the derivative, set it equal to 0. When you do this, you find the following. Delta t is equal to 2 e of r over m to the 1/3 power. This is just for Euler. So for every scheme you have, you can do this kind of thing. But here, this is specific for Euler. Okay? So you get this result. Now here's what's interesting. You might be tempted to think, well, look, if my round-off error is 10 to the minus 16, I can take a really small step. But look at this. This is to the 1/3 power. So you have e of r, which is 10 to the minus 16, raised to the 3rd. Okay, so it's 16 over 3. So it's around 5 or so. So if you take a delta t smaller than 10 to the minus 5, that's really not that small. Your round-off is starting to kill you. So for the Euler scheme, which is interesting, your global error is what? Delta t. So suppose you need a solution which is accurate to 10 to the minus 7 for whatever reason. Well, you might say, well, I'll just take its time step, which is 10 to the minus 7. Well, now you're starting to work over here. In fact, you can't get an error down to 10 to the minus 7 with Euler. Because once you get below 10 to the minus 5th, your error starts to go back up again because of round-off. Okay? So just don't lose sight of that. That this round-off is not just something that you can just, in practice, it doesn't, it's meaningless. It can mean something for you here. Okay, so that gives us an idea of error and how it grows. What are the issues concerning it? And again, most error analysis that is done for these schemes, all based on Taylor expansions. So what we want to do is say, okay, now that we have that in hand, now there's the issue of the stability, which is the other thing we wanted to consider with these schemes. Okay? All right. Now, one of the things that's very typical is this error type of analysis. We're going to do a little bit more of it later on in the class. Is that, this is what a lot of people do PhD thesis on in applied math or mathematics. I mean, you can spend a lot of time playing with different, remember there's a ton of variety of schemes you can come up with stepping. Well, then anytime, if you're into mathematics and you do numerical analysis, what you do is you come up with a new scheme and then you beat this thing to death. You go through and you do all this kind of stuff and talk about stability and accuracy and all this stuff, and that's, then you make a thesis out of it, and then you graduate, and then you go out and do some more of it. And 10 years later, you just find out that all you know how to do is math. It's terrible. Then you have your midlife crisis, and hopefully you have enough money for a sports car. If you don't, well, it's tough. I don't have enough money for a sports car, unfortunately. I still got like 5 years to hit it, but maybe if I win the lottery, I'll get the money for the sports car. We can hope. Stability. Okay, now here's the other side of the coin. You're doing an iteration process. So let's start off with something very simple. dy dt lambda y. This is a very trivial example, but it illustrates what we need to illustrate with this. With the initial conditions, now I can solve this exactly. It's a simple exponential growth. Y is equal to y naught e to lambda t. Okay, that's your solution to this thing. Okay. So now the question is, suppose I were to try to solve this on the computer. Well, I'd discretize it, and let's suppose you use an Euler scheme. If you used an Euler scheme on this, you would end up with the following iteration procedure. Simple as that. Here's your, remember, it's y of n plus delta t, f evaluated at t, which is just this. Now notice once I have that, I can pull out a common factor of y of n. I get 1 plus lambda delta t y of n. So I start off with y of n. I get to y of n plus 1 through this iteration procedure. Now suppose I'm going to iterate this n times, n steps. Well, actually, since it's such a simple iteration procedure, what you're going to end up with is something like this. After n steps, it's 1 plus lambda delta t to the nth power y0. My hope is that you can just see that from here. So suppose I start off at y0. y0 will give me y1 just by multiplying this. But then y1 gives me y2 by multiplying by this again. So I just keep multiplying by this every time. So that's where I get this to the nth power. So I start off with my initial condition. I iterate n steps. And so all I have to do is basically take this quantity, raise it to the nth power. That gives me my solution. Now remember that when you actually do this, you have some kind of error. Round off, whatever it happens to be. So really what you have, if you want to think about it, some amount of error that is also hitting this thing. Okay? So the question is, for instance, what happens to this error? And let's just consider this simple source of error right there. So my error will be E is equal to 1 plus lambda delta t to the n e. Okay. Now, a couple things to notice. For lambda positive and delta t positive, what happens? Well, if these are both positive, real positive quantities, then this is 1 plus something that's bigger than 1, or sorry, something that's positive. This is something bigger than 1 raised to the nth power as n goes to infinity. Then the error is going to go to infinity. That might not be such a problem, really. Because, in fact, if this is the case, what's happening to your solution? It's also going to infinity. Okay? And this makes sense. You basically, when you take n to infinity, you're saying, well, t goes to infinity. What happens to this? Well, it goes to infinity. Fine. So in this case, who knows? You can't really say much. Because that could be infinity, and this is like 100 times infinity, which is much bigger. Okay? All right. But in contrast, what if you have a situation like where lambda is negative? Okay? Now, if lambda is negative and delta t is positive, and they're both real, then what ends up happening? Well, your solution, if lambda is negative, delta t is positive, this becomes 1 minus a little something, so something less than 1 raised to the nth power. Well, if you have something less than 1 raised to the nth power and n gets big, this goes to 0. Okay? So this was for lambda positive. Now if lambda is negative, then this thing goes to 0. So your solution goes to 0. But let's talk about the error. Your error better go to 0 as well. But there's kind of two cases to consider. We don't necessarily even have to consider, for instance, lambda being a real quantity. Delta t we typically think of being a real quantity, but lambda could be complex. And really what counts is the following. There's two cases. This. What if the absolute value of this quantity here, which we're going to exponent, which we're going to basically raise to some power, is less than 1? Well, if that's the case, then our error goes to 0. If this thing's greater than 1, then our error goes to infinity. Simple as that. Okay? And by the way, case 2 holds for this case if delta t is equal to my. So for instance, if you have this kind of relationship, then you're in a situation where this scheme goes unstable, and your error grows. Your iteration scheme's unstable. Okay? So this is the kind of thing you would do when you do an analysis of the stability of a scheme. You say, I have a stepping scheme. If I do it under iteration, if I iterate this thing over and over, n times, where n goes to infinity, what happens to the solutions? And in general, you can develop this idea for any iteration scheme. So let's consider an iteration scheme which is a little bit more general than what we just did, which is I get my vector in the future is just the current vector times the matrix A. So I can do the same thing here. After n steps, what do I get? Now, one of the typical tricks to use on matrices that you're raising to the nth power is that you don't want to take this and throw it into MATLAB, take your matrix A and say, raise it to the nth power where n is like 1,000,000 or 10 or even 100. Okay, that's a little silly, partly because there's a very well-known result from linear algebra which says that is equivalent to I can rewrite that matrix in diagonal form times the matrix of eigenvectors. Okay? So this is a linear algebra result, which is basically take a matrix, and if I find its eigenvalues and eigenvectors, then the matrix of eigenvectors, its inverse multiplied by this matrix here, multiplied by this regular matrix of eigenvectors, is equal to A, where this matrix here is diagonal. And on the diagonals are all the eigenvalues of this, let's say, m by m matrix. Now, the nice thing, sorry, that's what that is. The nice thing about this is now if you say, how about if I take this matrix and raise it to the mth power? Or sorry, the nth power is what I'm using here. It's an m by m, but I'm raising it to the nth power. If I raise that to the nth power, all I have to do then is take the diagonals and raise them to the nth power. So instead of doing all this, more complicated linear algebra operations, all I have to do is raise those to the nth power. Okay, here's the observation to make. If I take this, I have this matrix, and if I can diagonalize it, so I'm just multiplying with some matrices, and then this is the important thing, is n gets big. What happens to this matrix? In particular, you know that this matrix looks like this. The only thing that matters right now, then, is if any one of the real part, any one of those eigenvalues is greater than 1. So if you take the real part of any of these eigenvalues, if it's bigger than 1, and you're raising something bigger than 1 to the nth power, what happens? It goes to infinity. The scheme is unstable. Okay? So this is the idea behind iteration schemes and looking at their stability. if you have these eigenvalues, and you're going to basically take these to the nth power, and if you're going to iterate something 1,000 times, 10,000 times, what you want to be sure of is that this isn't happening. Because if this is happening, your solution goes to infinity. Okay? So this is the price you pay for turning a differential equation into an iteration scheme. You've made this approximation, and in doing this approximation and making an iteration, not all iteration schemes are stable or converge or anything. Some of them blow up. And that's how you kind of do the analysis to tell if it's going to blow up or not. And from that, then you can either pick a different scheme, or if you know the conditions under which happen, sometimes it just means you have to take a delta t small enough so that that doesn't happen. Okay? So that's one thing that can happen, is you can take time. If you take a time step small enough, then you're fine. Take a time step too big, all of a sudden you violate this, boom, growth. Okay. By the way, you can easily generalize this to, for instance, if you had one of those Adams Bashforth schemes where you had multiple steps, where it not only depends upon y of n, but also a back point as well. You can do the same kind of type of analysis. Okay? So that's the typical stability analysis you do on an iteration scheme that comes from doing a discretization of an ODE or PDE. Okay. Now, let me erase this. And show you something important. Let's go back to this example here that we did. We talked about stability, about specifically the Euler scheme for that equation right there. The Euler scheme for this equation right here says, okay, so if I take this thing, I discretize, I get this formulation of the problem right here. And what I'm really interested in is if this thing is stable or not. And there's a criteria for checking that. The criteria is basically given by here. My error goes to infinity if this occurs, which is bad. I know I'm making a lot of mistake there, obviously, because my error shouldn't be going to infinity. My error goes to 0. That's desirable. Okay? So we have these two criteria based upon doing what's called this Euler method, or it's often called the Euler, because what's happening in this method is my future time is dependent upon my current time. We could also do what's called the backward Euler, and I introduced in the class at the end of the class last time. And the backward Euler is the following. Instead of discretizing like we did over there, okay, the backward Euler says my future point, the current point, plus delta t times lambda y of n plus 1. So now, instead of using the current point to evaluate my function f, I use the point in the future. Now, remember, this is now going to be implicit scheme. But this implicit scheme is fairly simple for this equation, right? Because I can move this over to the other side, and right, I can get y of n plus 1. I get 1 minus lambda delta t is equal to y of n. And so in the end, I get y of n plus 1 is equal to y of n over 1 minus lambda delta t. So if you think about going n steps, your solution, y of n, is equal to 1 minus lambda delta t to the nth power y 0. This is the iteration scheme for backward Euler. I want to point out how different it is from what we have for forward Euler. So take a look and simply compare that with this. At this point, you can't say anything like, this is better than that. Because this implicit scheme we developed actually was very easy. And for this specific case, we don't really have to solve a system. We have a direct iteration procedure, just like this one here. That one was from an implicit way of thinking about it. This is explicit, but they both turn out to be a simple iteration scheme. Now the question is then, we could ask, which one is better? From the point of actually doing accuracy, they're the same. We're both truncating. The truncation error is the same for both of these. Delta t squared over 2 times the second derivative. So now the difference is going to come in the stability. Look what you got here. Look what you got there. And now, if I let the following quantity be z, some complex number, be lambda delta t. So I'm going to replace this lambda delta t by some z, which is just going to be some complex number, because lambda could be complex. Then, for forward Euler, Fe, I find 1 plus z greater than 1 is going to be my problematic area, my unstable region. Whereas for backward Euler, I get 1 over 1 minus z greater than 1. That's my unstable region. Okay, so very different criteria. And how it manifests itself is really significant in the problem. And it actually shows you why people would actually want to use implicit schemes. So I'm going to plot out. Here is a plot in the z-plane, complex z-plane. So z real versus z imaginary. And what I want to plot here is the stable versus unstable regime. Stable, unstable. So if I take steps in which z is confined in this disk, that means my iterations, my forward Euler iteration scheme will be stable. Okay, that means, and I'm getting this disk by this, finding where that's true. So that's the boundary. And inside of here, it's less than 1. Over here, it's greater than 1. So that's what we get. So this is forward Euler. Okay. Backward Euler, a little different. Stable out there, unstable in here. So, from the stability point of view, backward Euler is amazing. All you have to do is avoid stepping in there. Everything else, this iteration scheme, is stable. And in fact, you can take really large delta t's, because it's going to put you in a pretty big circle. And it's stable. Not accurate, but stable. Okay? So the stability of the iteration scheme, when you look at it, backward Euler has incredible stability properties. Like I said, there's only a very small region here that you have to avoid stepping in, and as long as you avoid that, works like a charm. However, forward Euler, look what you got. You better be in that ball. If you're not in that ball, your scheme's going to go to infinity, you're going to get nonsense. So forward Euler has a very narrow range under which it's going to operate correctly. Okay? This is why, and this is, by the way, this kind of difference typically tends to be the hallmark feature of implicit versus explicit schemes. Explicit schemes tend to be more like this. I have a ball under which stability is going to work. Make sure to hit that ball. There it is. Implicit schemes typically have a ball under which it's not going to work, but then everything else is going to work. The problem is that typically to do this, you have to solve some kind of nonlinear system of equations. In this simple example, we didn't have to do that. So you pay a price, often, to have to do this. But the point is then, look at the time steps you can make here. It's incredible stability properties. Okay? So whenever you have a scheme that you're going to be working on, these are the kind of things you're going to have to make sure to always just at least keep somewhere in the back of your head, that there is this idea of stability, there is this idea of accuracy, that are trying to balance each other off. In practice, we're typically going to use schemes that are going to be fine for stability. Okay? So we don't have to think about it that hard. And mostly we can concentrate on accuracy. But it is something that's underlying any kind of scheme you develop. You better be aware that these are issues you have to think about. Okay? Don't blindly just, I'll just discretize go. Well, if you discretize and go and you're right there, you're never going to get it to work. Okay? All right. That's it for today. Download the notes, and homeworks will be up by the end of the week, and we'll go from there.